Okay. Hi, everybody. Today we have Dave Gorrell. He lives in Maryland, born in 1939. He started watch repair in 1970, 1962 at Montgomery Ward's.
Wow, 62?
1962, Montgomery Ward's. He retired from watchmaking in 1979. He opened his own clock shop in 1964. He was a school teacher for 38 years. He still, to this day, repairs over 200 clocks every year. He founded the one-day class on clock repair for Chapter 1. He is the chairman of the Ward Bransalon Time Symposium. He is also he is the overall chairman of the Mideastern Regional 5 times. And he also became a field suitcase workshop instructor in 1982. He still teaches classes at the Horology in Columbia, Pennsylvania. He is here to do us a presentation on the search for longitude. So take it. Oh,
There you go. Okay, the search for longitude is the voyage of 400 years, a story of 40 years of trial and error spiced with intrigue and, in some cases, people believe chicanery. Dana Zobel, who wrote a very good book on the search for longitude and Harrison's problems with the board of in England. She hits more toward the chicanery side of it than I do. Okay, well, the age of exploration. Oceanic exploration and trade began in earnest after the fall of Constantinople in 1453. That was one of the most pivotal dates in history. It set a need for accurate navigation techniques, which became at this time a necessity. Cartography became a matter of national concern to many or to any naval power. Now, you might want to ask yourself, why was this such a traumatic event in world history? Well, you can see that Constantinople, which now is called Istanbul, controlled any trade between the Black Sea, the Mediterranean Sea, and trade with Asia. The Ottoman Empire in the 1300s was this size, very small. There had been a 700-year period of expansion of Islam, and you can see that with these maps. By 1500, you can see the Mediterranean had become a Muslim lake. From Spain to Lake Baikal was all Muslim territory. Christians were not involved or not appreciated in any way. All the orange, purple, yellow is Muslim territory. The whole north coast of Africa and most of the Eastern Europe. There were two major incursions of the Muslim faith into Europe during this period. One ended at around 700, but they retained their control of Spain to 1492, which is a pretty poignant date for most of us. Okay, now, all the trade routes from Asia to Europe were severed by this event. By 1500, most of the trade with Asia had been curtailed and controlled by the Muslims, which forced the Europeans, especially the northern Europeans, to look west to the Atlantic Ocean. Now, trade in the Mediterranean is one thing. Trade on the North Atlantic was a whole different ballgame. You were never more than 3 days away from land anywhere on the Mediterranean Sea. So you really didn't need longitude. When you get into into large bodies of water like the North Atlantic, knowing where you were became a real problem. So they developed a system of a means of identifying where you were by latitude and longitude. Latitude, as you can see, are parallel lines that run east and west, north of and south of the equator. Longitude, on the other hand, are meridians or lines that run from pole to pole and start at the prime meridian. Latitude. By the way, if you do have a question, just don't hesitate to ask. Latitude is used to determine the distance north or south of the equator. It was standard and in common use by AD 15 or 150. And can you see this instrument?
Yep.
Yep.
Okay, this is an astrolabe. It was invented by the Arabs and used to determine their positioning and latitude on the deserts. Traveling on the desert is very much like traveling at sea. You don't have any landmarks or very few landmarks by which to use to identify where you are. Latitude can easily be determined by measuring the sun or known stars above the horizon. You can do it yourself. If you are in an area where you can see the horizon and the North Star, hold your fist out to the horizon till it rests on the horizon, add your fists, count the number of fingers, and each finger is 2 degrees of latitude. So it's very simple to find latitude, and it was no problem during this period. Longitude, on the other hand, is a different story. It's a function of time. The Earth takes 24 hours to complete one full revolution of 360 degrees. Therefore, 1 hour of time equals 15 degrees of longitude. 1 degree of longitude equals 4 minutes of time. How was longitude determined in these early days after the Muslims had pretty much closed the Mediterranean and seafarers were forced out into the North Atlantic? It was not. Ship's captains used dead reckoning to attempt to establish or estimate their positions. It was merely guessing. Basically, they sailed to the desired latitude of their destination, then sailed east or west until they sighted their destination or something that looked like it. Now, that's very important. Something that looked like it. We'll see how that pans out later. So time equals distance. 1 hour of time equals 15 degrees of longitude, which corresponds to 1,000 miles at the equator. However, lines of longitude or meridians are not parallel, but converge at the poles. 1 degree of longitude equals 4 minutes of time the world over, but varies in distance from 86 miles at the equator to 0 at the poles. How to use one of the people knew what to do. They just didn't know how to do it and didn't have the tools with which to do it. If you knew the time of the port where you were leaving and you sailed, say, for 4 hours, and you looked at the time would be different. If you subtract that time from the time it was when you left the port, you could tell where you were. The only problem was they had no idea or nothing accurate enough to perform that function. There are 3 basic approaches to this problem of finding longitude. especially when you have absolutely no landmarks. One is terrestrial. There was none. At sea, there's no possibility. The other is celestial, the stars and the moon. The third is mechanical. If you could find a timepiece you could use to compare a time at your base and the time of where you were, you could determine your longitude. But each had its own unique inherent shortcomings. Celestial The two methods seem the only likely possible solution. Celestial, the lunar distance method. We'll explain that later. Favored by scientists and naval institutions. Mechanical, some sort of timepiece that kept accurate time at sea. But what sort of accuracy? Most of the watches in those days, we're talking about the 1700s, we're 99% accurate. That means that 86,400 seconds in a day equals to an error of 864 seconds, or almost 15 minutes. So the best watches of the day were accurate only to within 15 minutes a day. Well, you might say that's not much. However, a 99.99% accuracy equals an error of 8.6 seconds a day. Here again, doesn't seem like much, but what are we dealing with? At 38 degrees north latitude, about the same latitude as what we are today, 1 degree of latitude equals approximately 364,000 feet, or 69 miles. 1 minute equals 6,068 feet, 1.15 miles. 1 second equals 101 feet. Longitude, on the other hand, 1 degree of longitude equals 288,200 feet, or 54.6 miles. 1 minute equals 4,800 feet, or almost 1 mile. And 1 second equals 80 feet. So how accurate must an instrument be to give you reliable longitude? A 15-minute error was equal to 13.6 miles per day. A 8.6-minute error was equal to 7.82 miles per day. Multiply the number of days in a voyage, only compounded the problem. The average crossing, say from Liverpool to New York, was 20 to 25 days. Therefore, a timepiece that was 99.99% accurate would provide an error of 156.4 miles, which means that you are approaching, say, for example, the coast of North America, you could be off as much as 154 miles, which isn't very accurate at all. There was a need for an accurate timepiece. Determining longitude at sea required the accurate comparison of time from some standard position to the traveler's current position. Like we said before, the problems that had to be solved in order to get this sort of accuracy. An accurate timepiece that was impervious to the motions of a ship, an accurate timepiece that was impervious to changes in temperature, barometric pressure, variations in gravity, and humidity. A lubricant that would withstand conditions at sea. Up to this time, the primary lubricant was whale oil. which is a product that doesn't hold up very well. How to spur innovation. How to get someone to come up with a device that could produce an accurate longitude reading. In 1598, King Philip II of Spain established a prize of a pension of 6,000 ducats. That would amount to about $1,600,000 in 2019 dollars. In 1610, the Dutch Republic offered a 30,000 florin prize. That would be about $1,800,000 in 2019 dollars. Now, you might ask yourself, why would these rulers put up so much money for this? There had to be a reason. Well, one of the problems was if you didn't know where you were longitudinally, you couldn't enter a port at night or during a storm or at any time where you couldn't see the coast. And very often, if you got to see the coast and in a sailing ship, you could be stranded and run up on the rocks with very little chance of survival. But there are three things that motivate people: sex, power, and money. One of the things that the Arabs, when they took over North Africa and the Levant, the Middle East, is they cut off all trade with Asia, which included sugar. Now, Columbus discovered the West Indies in the Caribbean area in 1493 or 1492. In 1493, sugar was introduced into the Caribbean islands. Sugar was, if you had control or owned a sugar plantation in one of the West Indies islands, it was like having an oil well in your backyard. Millions of dollars were made in producing sugar in the islands and sending it back to Europe. Unfortunately, there were some negative side effects to that. We hear about that all the time. One was the sugar production decimated the Indian population of the Caribbean. It also encouraged and not encouraged, but actually forced the slave trade with Africa. So it was this desire for money and the production of sugar, which led to the motivation behind all these prizes. Now, England did not enter into this. They were busy with other things, and it took something else to motivate them. They were very interested because they were engaged in the fishing trade off of Newfoundland, North America, which was okay because you weren't any more than 3 days from land if you took the northern route from the Orkney to Iceland, to Greenland, to Labrador. You got to the Grand Banks. They didn't need navigation for that because they weren't landing. But sailing down to the Caribbean was a whole different ballgame. So, October 22nd, 1707. Tragedy off the Scilly Isles. Admiral Sir Cloudesley Shovel, commander of the White Fleet in the Mediterranean, was ordered from the Mediterranean back home to Plymouth. He set sail, went through the Straits of Gibraltar, turned north through the Bay of Biscayne, and headed toward England. They hadn't seen the sun in 14 days, so they had no idea where they were. They sighted land and Shovel, not knowing pretty much where he was, nor did the other captains, he got together and the fleet had a meeting. The captains agreed that this was the land that they had sighted was actually the Usan, the coast of France. Down here, you can see it right near where Brittany, the coast of Brittany, there's Usan. However, he wasn't there. What he saw were the Scilly Isles. He could not tell how far east or west he was from the coast of France or the coast of England. So he saw land and he ran into the Scilly Isles. Now, the Scilly Isles are right, as you can see, to the right or to the left on your screen, off the coast of England, treacherous waters. What he was using was dead reckoning, recognizing the land. Dead reckoning proved all too deadly. The HMS Association, the HMS Eagle, and the HMS Rodney were sunk. 1,647 lives were lost. Well, that created quite a stink. So it spurred the English to start to join this group of countries trying to find some means of determining accurate latitude. So they established the Longitude Act on July the 8th of 1714, established during the reign of Queen Anne. There were 3 prizes. The first prize was £20,000, 4.7475 million in today's money. But you had to determine longitude to an accuracy of 1/2 a degree. There was a second prize, only £15,000. Determine the longitude to an accuracy of 2/3 of a degree. The third prize, £10,000. Determine longitude to an accuracy of 1 degree. Now, remember what 1 degree error was like? Okay. So what sort of accuracy was needed? The third prize, 1 degree, 54.6 miles over 20 days with an error of no more than 18 seconds per day. 54 miles. In other words, if you're coming up to the coast, you don't know whether you're 54 miles too far to the east or too far to the west. Second prize, 2/3 of a degree, 36.4 miles over 20 days, an error of no more than 13.5 seconds per day. The first prize, 1/2 a degree, 27.3 miles over 20 days, an error of no more than 9 seconds per day. Now, if you're coming up onto a coast and it's stormy or the seas are rough and you don't know whether you're 27 miles east or too far west of your destination. So you're actually still going in almost half blind. So the Board of Longitude was established. It lasted from 1714 to 1828. It was tasked with determining the accuracy and validity of any and all submissions and claims to the prize. And of course, the prize with that much money brought in some interesting people. There was a blue ribbon panel, the First Lord of the Admiralty, Speaker of the House of Commons, the First Commissioner of the Navy, the professors of mathematics at Oxford and Cambridge, and the President of the Royal Society. These were big name people in England at the time. Some proposals. The harebrained. James Squire devised the system, divide the sky into 1.25 million cloves or spaces, which impossible. Humphrey Ditton, sound cannons at specific times from specific reference points. He suggested we anchor ships 600 miles apart across the Atlantic and fire cannons at specific times so that people could tell where they were. Evidently, they had no idea the depth of the Atlantic or the condition of the Atlantic during winter months. Winston Ditton had a fleet of ships anchored across the Atlantic at 600-mile intervals to fire cannons and rockets to indicate known positions. And then we have Digby's daft dog solution. He noticed that injuries, dogs with injuries healed at a certain rate. So what you would do is you would purposely injure your dog on ship, and as the dog healed, you could somewhat predict the time. No, the not so harebrained. The Galileo's eclipse of the moon of Jupiter. The moon, several moons of Jupiter that go behind the planet could be used as a timepiece. However, finding them on board a ship was impossible. Sam Flyer's star-spangled meridians. Here again, lining up the meridians with the stars. But here again, on a ship that is bouncing across the ocean, especially with cloudy days and storms, not very successful. Jeremy Thacker's chronometer. Well, he developed a chronometer that was quite accurate, but not accurate enough to make it worthwhile at this time. Johannes Werner's lunar distance method. Now, this one caught everyone's attention, at least in the scientific and mathematical community, because it considered using the moon and the distance from the moon, the center of the moon to various stars could be used as a clock, because the moon travels across the sky at a pretty steady rate, and it could be used. However, that produced its own problems, which we will talk about in a moment. This lunar distance method was championed by Neville Maskelyne. Now, Neville Maskelyne, if you read Zobel's book, is the villain in this, but he really wasn't, in my estimation. We'll talk later about that. Most members were skeptic. Sir Isaac Newton, president of the Royal Society, Edmund Halley, astronomer and naval expert, Samuel Clarke, theologian and mathematician, and all of them doubted whether a mechanical nor a celestial method could be refined enough to be useful. So these were the people who were leading the board of trade or the board of longitude, and they were skeptical going in. Neville Maskelyne, 1732 to 1811, became the head of the Royal Society, and he championed the lunar distance method. What you did from your ship, you measured from the edge of the moon to a star, and since it's so far away, it would be the same, for example, in London or Bristol. And what you could do is determine the same time in Bristol, the same time as here. You could come up with a set of calculations that would determine your longitude. Although there were problems with the lunar distance method. First, an extremely good backstaff or sextant was necessary. Getting accurate sightings of the moon or sun on a ship at sea is difficult. Calculations took up to 4 hours using spherical trigonometry. Correcting for parallax and refraction, because if you look at an object through a fluid, air is like a fluid, there is refraction. It bends the light and you don't get an accurate position. Correcting for semi-distances of the Earth and the Moon, in other words, your calculations are set on the center of the Earth and the center of the Moon. You have to allow for that because you're on the surface of the Earth, not in the center. And you also had to consult a nautical almanac. Plugging this data into the following formula to get your results. Now, that is the formula that every ship captain had to use while determining their longitude with lunar distance. Most sea captains did not have the mathematical ability to handle this type of calculations. And it took 4 hours to put it all together. And there were errors in the nautical almanac. You are predicting the position of the moon days, weeks, and months and years ahead. So at the time, the lunar distance method was no better than almost dead reckoning. But it was improving. Few sea captains could handle the mathematical skills needed to make this system work. The sextant, which had just been invented around this time, was a great help in sighting the moon and the sun and the stars. This is a page out of the Nautical Almanac at the time, and of course there were errors. Now, we get to the watch and clock part of it. John Harrison, born March 24th, 1693, died March 24th, 1777. An amateur to the rescue. He was born in Yorkshire, the eldest of 5 children, on March 24th, 1693. Family moved to Barrow on the Humber River when he was about 4 years old. He was taught woodworking by his father. He was basically a carpenter or a joiner. He was extremely interested in mechanics and physics. This shows you where his birthplace and where he lived. Most of the big names in astronomy, mathematics were in London. Also, clockmakers were in London. And he's out in the boondocks, far away from everywhere. Here's the city of Barrow and his home, right? You can see that on the chart. He was also an amateur horologist. He built his first pendulum clock in 1713 at the age of 20. Built 2 more in 1715 and 1717. Built the tower clock at Broxleyby Park in 1722. It has been running continuously for more than 270 years. It requires no lubrication, therefore no cleaning. The last time it was checked was I believe it was 1953, and has been running ever since. He also developed the gridiron pendulum and the grasshopper escapement. This is a picture of his home. This is a picture of his clock. Now you will notice, if you look carefully between the plates, they're wooden wheels. They're wooden works. Yes, most of his early clocks were wooden. And he used, as bearings instead of bushings, he used lignum vitae, which is a very oily, very hard wood, and hence the longevity. And he'll use that when he starts his other experiments. Here's a look at some of the wheels. You can tell they're nicely wooden works. Here is some of the wooden works. Now, he used a very interesting system. Whereas in American woodworks clocks, the wheel and the teeth are all the same piece. Not in his clocks. They were segmented and placed and put in place this way. Reduced wear and also reduced the amount of breakage. The grasshopper escapement is almost friction free and works very well. Here's another example of a single pivot grasshopper escapement, which he used in his clocks. The gridiron pendulum, compensating for temperature and variations. He is the first one to come up with the coefficient of expansion idea of different metals, namely brass and iron. And he noticed that if you alternated the rods in a pendulum between brass and steel and left them open at one end, the expansion and contraction of the pendulum would be compensated for, and there'd be no change in timekeeping. This shows how it works. Also used zinc. The clock tower at Brocklesby Park, still in existence, still working to this day, and with wooden works. So in 1735, Harrison decided, with the help of Graham in London, to tackle this longitude problem. He made his first sea clock in 1735. And here is a picture of it. Another picture of it. The two balls with the springs were used to compensate for the rolling of the ship. You see in the middle of the clock, the gridiron pendulum or gridiron device that compensated for temperature changes, barometric pressure changes. And this is how the system worked. You can see on the small yellow gears, the axles are actually supported by a crossed brass set of levers that reduced friction. And the two swinging arms were used to offset any motion of the ship that would affect the timekeeping. This is an example. This is the picture of the compensating device that he used. Quite elaborate. Here is how he reduced the friction in the pivots. All were rolling. Here's his drawing of the two barbells that acted as pendulums in tandem. He also had maintaining power, which meant that when winding the clock, no power would be lost, and adding to the accuracy. So H1 looked like it would be successful. So they gave it a sea trial. Harrison's sea clock was tested aboard the HMS Centurion on a voyage to Lisbon. Now, the interesting thing is that Lisbon longitudinally is not that far from England, but it is far enough to make the somewhat of a comparison. The return trip on the HMS Orford showed the accuracy of the sea clock. It was well within the accuracy required by the border longitude, but only for the third prize, not for the first or second. So Harrison was not happy. So he, in 1741, began working on H2. You can see that it also had the two pendulums, barbells swinging back and forth, but there were other changes he made to two that he hadn't used in one. One where instead of using the roller bearings, he made these, which, if you look closely, are ball bearings. The first time ball bearings had been used in horology. Here's another look at the H2. He was not that happy with the results with H2. So he began on H3 in 1760. Now notice he changes from the two barbells swinging back and forth to a circular balance wheel. And he also, if you look right below to the on the upper left-hand corner, that device is the temperature compensating device. Here's what H2 looks like for real. And this is the device he made. It's a bimetallic strip to compensate for temperature variations. A steel strip covered with a brass strip. They're welded together, and temperature changes are registered as the temperature affects the coefficient of expansion of each of those two metal strips. Here's his drawing of H3. He almost immediately realized this wasn't going to work. Here's another picture of it. You can see that compensating pendulum on the between the dial and the plate that holds the balance wheel. Another view of it. Now, here's H1 working. You can see how the the pendulums swing back and forth. They're connected by the spring. You can also get a very good idea of the size of H1. And here is H2. This is the rear of it. And here is H3. Unfortunately, H3 was not working at the time I was at the museum. So if you look very carefully, you'll see down on the right hand near the base, there's the click spring that came off and spun the clock down overnight. So it wasn't running when we got there. And they wouldn't open it up and repair it while we were there. So back to H2 again. You get a very good idea of the size of these things. They're not small. Another view of H1. Okay. So Harrison was not happy with H1, H2, or H3. So he began to work on something else. He knew that the H3 was not going to work, at least to his satisfaction. In the meantime, he commissioned John Jeffreys in 1753 to construct to his specifications and designs a watch for his personal use. And it was at this point, I think, that Harrison had an epiphany. The epiphany was that he was thinking of a sea clock when he should have been thinking about, as he realized, a sea watch. That one of the things that you can combat the action of the ship, the temperature and humidity, gravity changes, was increasing the oscillation frequency of the timepiece. Now, where he got that idea, I don't know. I talked this over with Rory McElroy, our present director. He doesn't know either when this occurred, but in between 1740 and 1753, Harrison had the change of heart. So in 1755, Harrison began to work on his new sea watch. Number 4 was ready for sea trials in 1761. And this is the watch H4 1759. Better view of it. It's only about 4.5, 5 inches in diameter. It's like a big pocket watch. But it was like no other pocket watch that had ever been made up to this point. This is what the inside looks like. You can see the intricate engraving and piercing. Another drawing of it from his work. This is what the watch looks like with the front plate off. It uses a balance wheel, very small hairspring, but it beats 5 times a second, increasing the period of the frequency of the oscillation to what we now consider normal is 18,000 beats per hour. And that seemed to solve the problem. This is the interior of the watch. The key component, though, was the escapement. The escapement was a virgin fillet. Crown wheel escapement. And you can see on the next slide the 2 diamond impulse faces that he used to reduce wear, and that helped produce the accuracy of it. This is also the maintaining power and type of. Okay, one thing that Harrison learned when he took H1 on its sea voyage, he was not a sailor. He was seasick the whole time to Lisbon and the whole time back. So when the sea trials came for H4, he sent his son. And William set sail with H4 for Jamaica aboard the ship Deptford on November the 18th of 1761. Upon arrival in Jamaica in January the 19th of 1762, the watch head was only 5.1 seconds slow. Unbelievably accurate watch for the time. Well, everyone thought it was a fluke, especially those on the board of Longitude. So they ordered a second sea trial. William again set sail for Barbados aboard the Tartar on March the 28th of 1764. That watch had an error of only 39.2 seconds over a 47-day period, well within the parameters of the prize, the first prize from the Board of Longitude. However, they were still, Masculine and the others were still convinced this was a fluke. Yes, it was a very accurate watch, but could it be useful? In other words, could it be reproduced? Here's the map of the voyage from England down to Barbados. The second sea trial was an outstanding success. Did he receive his justly won prize? No. The skeptics had their day. Well, not exactly. There were a few hitches. Chicanery rears its ugly head, or so some think. The Board of Longitude changed the rules, implying that the successful sea trials were a fluke. They ordered Harrison to turn all models of his sea clocks to the board. That means H1, H2, H3, and H4. Disclose all his secrets. Make 2 more watches and have them tested. Have H4 copied by another watchmaker and tested. In exchange, he would get £10,000 and the rest when the tests were successfully completed. Harrison took umbrage at all this. He thought he should be taken at his word. However, the watch was given to Kendall, and Kendall began making a duplicate. And Kendall's watch went with Captain Cook on his voyages through the Pacific, and Captain Cook agreed that the watch was indeed the answer to the problem of navigation. He received £2,000 over the span from 1841 to 1755 for continued construction, completion of H2 and 3. From 1760 to 1765, Harrison received £2,865 for various expenses related to the construction, ocean trials, and eventual award for the performance of Sea Watch 4. Despite the performance of H4 exceeding the accuracy required of the highest reward possible in the original Longitude Act, Harrison was rewarded £7,500, that is 10,000 minus payments he had received in 1762 and through 64. Once he revealed the method of making his device and was told that he must show that his single machine could be duplicated or replicated before the final £10,000 were paid. Harrison made one rather than the requested 2 further copies of H4, and he and his family members eventually appealed to King George III after petitions for further rewards were not answered by the Board of Longitude. A reward of £8,750 was granted by Parliament in 1773 for a total payment of £23,065, spanning 36 years of Harrison's work. And King George, the guy we fought against in the Revolution, had come to his rescue. This is a timeline of the development from Harrison's first visits with Graham until his final payment. Here is what he produced: H1, H2, H3, H4, and H5, the duplicate he made after H4. He died shortly thereafter. His sons received most of the benefit of his work. This is his gravesite, which was restored in 1879. Now, when Masculine requested all of Harrison's work, that is H1, H2, H3, and H4, plus all his secrets. They came to his house uninvited, unbeknownst to Harrison, and with a cart, unsprung cart. And they loaded all of the C clocks onto the cart, dropping H1 on the ground. They went to the Admiralty and they were locked in a closet for years until a gentleman came into it. Now, so in the meantime, the longitude problem was solved, right? No. Why? Chronometers were always expensive. Harrison's H4 was estimated to cost around 450 pounds. That's equivalent to $10,000 today. Now, what sea captain and what government is going to spend $10,000 on every ship? And by the way, you don't need one chronometer, you need two. Because if you have one chronometer, you have an idea what time it is. If you have two, you have a better idea. Most large ships, after they began to use chronometers in the 1840s, carried three. So if one was out, the other two could be used as correction. To guarantee their accuracy, ships really needed more than one chronometer. It wasn't until the 1840s that naval vessels began to use chronometers. Commercial vessels used them even later. So dead reckoning was used up until the 1850s and 60s, even though there was a means for determining longitude quite accurately. What system would be used? The lunar distance system. As time went by, the tables became more accurate and would work. Chronometers were expensive, but easier to use. But there were too many problems, as stated earlier. Why then did it remain in contention? As a matter of fact, the lunar distance method is still used. Even though we use satellites for timekeeping now, what happens if the satellites are damaged or come under attack from an unfriendly nation? You have to have some reason to go back. One of the reasons the lunar distance system was used is that it worked extremely well on land, which helped map makers, because not only did you have to have an accurate determination of longitude at sea, you had to be sure that the port you were heading for was accurately located on the map. So maps were updated using this method. Now, remember the damage to H1 as masculine took everything back to the Royal Society? Lieutenant Commander Rupert T. Gould, naval commander, had a bad war in World War One, but he found these machines and decided to devote his life to getting them back in operating condition again. And it's to his efforts that we have them today. So the list of the awards amount for the search for longitude, it was expensive. It was long drawn out, but it worked. You can see most of this still in the National Maritime Museum in Greenwich. Thank you very much for listening.
Thank you. Does anybody have any questions? No? Well, that was very, very informative, very interesting. I liked it a lot.
Uh,
Anybody have anything else to add for today? We're gonna have to get out of here pretty quickly. Don't forget your clocks.
Okay, well, thank you very much for
Thank you so much.
your patience.